This video covers Taylor's theorem, and unlike many other videos I do, I usually have all the important points and maybe one or two slides. When we do this, when we approach this Taylor's theorem, we're going to approach it in stages. So there are many different little points along the way, but this is probably the best review I could come up with. But essentially what we're going to do is start with Taylor's theorem for single variables. That's what you did in regular first year calculus. Then we'll do a first order Taylor formula for multivariables, many variables. And then we'll do a second order's Taylor formula for multivariables. So these are kind of the heart of our video. But we also talk about this Hessian matrix, which you'll see later. So it's important not just for this chapter, but you'll see it later as well for min and max. So it's good to be familiar with those. And then we'll talk about second order Taylor's formula for several variables. And with that, we'll talk about the Hessian, and we'll do some more examples. But we'll start by reviewing Taylor's theorem in one variable, something you might have seen either in high school or in your first year college calculus class. What the Taylor series allowed us to do was to approximate a function f with a polynomial or a power series. If we want to approximate a function with the polynomial, and we want to approximate that function in the neighborhood of a, so somewhere near a, so this approximation is good for a small area in the vicinity of a point a, we can certainly evaluate the function at that point a. That would be our first approximation. Our next approximation is to evaluate a at the first derivative and multiply times x minus a, and this will give us a linear approximation. We can then go for a quadratic approximation by evaluating a at f double prime divided by 2 and then multiplying by x minus a squared to give us the quadratic approximation, and we would add it with the f of a and f prime of a x minus a. We can keep doing this. We can take the kth derivative, evaluate at a, divide by k factorial, and multiply by x minus a to the kth power. So we could get a kth degree approximation. And then if you go out to the kth term, your error, so your function is equal to pk plus a remainder, or your error, and that would be your kth plus 1 term, your k plus first term would be your error. We can use these ideas to do this example. We want to approximate natural log of x, which is this curve in blue over here, at the point a equals 1, so over here. This is where we want our approximation to be good. So the first thing we do is we evaluate at f of a, so a is equal to 1, so we take natural log of 1, and that is equal to 0. Then we take the derivative, the first derivative, evaluate at a, and multiply x minus a. So the first derivative of natural log of x is 1 over x. We evaluate that at 1, and we get 1. So now our first approximation, our linear approximation, is going to be our 0, our f of a, plus f prime at a, which is 1, times x minus 1. That's our x minus a term. And that gives us y is equal to x minus 1, which is this line here. So that's our linear approximation of our blue curve natural log of x. But we can make a better approximation, a quadratic approximation, by taking the second derivative. So the second derivative of x, of f of x, is equal to minus 1 over x squared. And if we evaluate that at a equals 1, we get negative 1. So our second degree polynomial is going to be our 0, our f of a, plus our f prime of a times x minus a, times f double prime at a over 2, so f double prime is negative 1 over 2, times x minus a squared. So here's our quadratic approximation, which is this curve here, our polynomial. You can see you're getting a little closer to a curve, and if you want an even closer approximation, you would take the third p3 of x, and so you would have to take the third derivative, divide by 3 factorial, and multiply by x minus a to the third. And you can also see, as long as you're near A, you'll get a pretty close approximation. And of course, the further away you get, the larger the potentially larger error. This next example talks a little bit about the remainder term. So if we took the fifth order Taylor polynomial of f of x cosine of x about x equals pi over 2, this is our approximation, our polynomial approximation. So our remainder is, for our estimate for our kind of error term, we're going to take the sixth term of our polynomial, and that's going to end up being minus cosine z 6 factorial x minus pi over 2 to the sixth. And since cosine is less than or equal to 1, that gives us a boundary for our error approximation. In other words, it's going to be bound. It's going to be less than or equal to 1 over 6 factorial x minus pi over 2 to the sixth. Now we're ready to talk about the first order Taylor's formula in several variables. So we're going to have several variables, and then the first order meaning we're only going to a polynomial of degree 1. So we have our f of a, just like our normal Taylor's formula, plus, and instead of just the first derivative, we're going to have the derivative matrix, or another way of notating that is the gradient of f evaluated at a times x minus a. So you can see the parallel. The formula we will be using to estimate a function f is our polynomial estimate will be f of a times the derivative of f of a, and notice this is a derivative matrix, x minus a. So we'll take a look at an example. I wrote the formula up here so we can do an example. We have a function f that takes 4 variables, x1, x2, x3, x4, and it produces this scalar here. We want to approximate this function at a equals 0, 0, 0, and b equals 1, 2, 3, 4. So the first thing we need is our f evaluated at a. So first we have f evaluated at 0, which is just 0, and f evaluated at 1, 2, 3, 4, so we plug in 1 for x1, 2 for x2, 3 for x3, and 4 for x4, and we get 54. So first we need to take our partial derivatives, our first order partial derivatives. So df with respect to x1, here we have 1. This is 0, 0, 0, plus x2, x3, x4. When we evaluate that at 0, 0, 0, we get 1. df2 at x2, so looking here, this is 0, this will be 2. This is 0, this is 0, and here we'll have x1, x3, and x4. Evaluated at 0, we get 2. Similarly, you can see that df3 is going to evaluate to 3, and df4 is going to evaluate to 4. And then we can plug into our p1, our 0, 0, 0, 0. We get our function f of a at 0, which is 0. Our f of dx1, which is 1 times x1 minus 0, plus df2 of d of x2 is equal to 2 times x2 minus 0. df dx3 is 3 times x3 minus 0, and df4, which is 4, minus x minus 4. To do the calculation at 1, 2, 3, 4, so that's p1 at 1, 2, 3, 4, so I need to evaluate dfx1 at 1, 2, 3, 4. So this is the dfx1 is equal to 1 plus x2, x3, x4, and evaluated at 1, 2, 3, 4, so that would be 1 plus, oh, this should be multiplied, 2 times 3 times 4, so that would give me 25. And I fixed this to the multiplied sign. Now if I look at dfx2, that's 2 plus x1 times x3 times x4, so evaluated at 1, 2, 3, 4, that's 2 times 1 times 3 times 4, which gives me 14. Now plugging into this formula, and I just want to make sure we understand just this part of the formula. So our approximation is going to be f at x naught, which we had calculated here, which is 54. And then we're going to take the sum from 1 to n. That's the number of variables we have. So we have 1, 2, 3, 4 variables. So we're going to have 1, 2, 3, 4 more terms from this summation. We start with I equals 1. So we're going to do d of x1 at x naught. So we calculated that here. d of f at x1 is 25. And then we need to multiply it by h1, which is equal to x minus x naught, looking at this formula on top. So that's going to be x1, because this is our first variable, and then from 1, 2, 3, 4, we're going to subtract the first variable, minus 1. Now, the second term of the summation, I equals 2, df x2, we calculated the result here as 14, and we evaluated it at x naught, and then we need to multiply by our h2. So that will be our second term, our x2 minus our second coordinate. And then I didn't calculate dfx3, but it will equal 11 once you evaluate it at 1, 2, 3, 4. And then you need to multiply by h3, which is going to be x3 minus our third coordinate, and then our dfx4 evaluated at 1, 2, 3, 4 will give us 10, and then times h4, which is x4 minus our fourth coordinate. So this will be P1, evaluated at 1, 2, 3, 4. I have this alternate form of this formula here, which instead of having this summation here, you can express this as the derivative matrix of f evaluated at a times h, where h is equal to x minus a, as we had done here for h. And then so this is the alternate form of the first order Taylor polynomial. This next topic of differentials is one that is often skipped, and we are going to skip this as well. Next, we're going to look at second order approximations for our surface. And the tangent plane here is our first order approximation. So here we have a surface, this bell surface, and this blue kind of plane is our tangent plane. It's tangent at this point, AB, and it's a good approximation, especially very close to the point AB. But we can improve this approximation by looking at quadratic surfaces, something with more curves. So in other words, we're going to introduce the second order variables. So we can have x squared, y squared, and x times y. So now we can have a quadratic surface to approximate this, this surface at this point. The formula for the second order Taylor formula is written here. So we have our summation of our first order derivatives, and then we're going to have the 1/2, sort of the other coefficient, similar to what we had for one variable, and then the sum of our second order derivatives times x minus a I, and xj being the y term, or the y term, minus 8j. So let's do an example. So if we have f of xy is equals cosine x cosine y, and we're going to evaluate this at 0, 0, and we're going to find the second order Taylor polynomial. We are going to start with f of a, so f of 0, 0 is equal to 1, and then we're going to look at our first order partial derivatives. So first order partial derivatives is negative sine of x cosine of y, and we plug in 0, 0. Again, the first order partial derivative with respect to y gives us minus cosine of x and then sine of y. Plug in 0, 0, we get 0. Working with the second order partial derivatives, f of xx, that's the derivative with respect to x of f of x. So that will give us minus cosine y, since cosine is considered a constant. Derivative of minus sine of x would give us minus cosine of x. Evaluated at 0, 0, this will give us negative 1. F of y, so taking the derivative now of f of y with respect to y, we get the derivative with respect to y, cosine x sine y. So now cosine x is considered a constant. Derivative of sine of y is cosine y. Evaluated at 0, 0, this will give us 1. Then last we have f of xy, which is the derivative with respect to y of f of x, which is derivative of respect to y of minus sine x cosine y. So now our minus sine x is considered a constant. Derivative of cosine y is negative sine of y, so we get sine x sine y. Evaluated at 0, 0 equals 0. Finally, we plug into our formula for P2, which is f at a, which is f of 0, 0, and then our first order partial derivatives. So that would be f of x evaluated at 0, 0, then x minus 0, plus f of y evaluated at 0, 0, y minus 0, and now all our second order partial derivatives. So running through the double summation seems kind of unnecessarily difficult, but what you want to remember is you have two variables, x and y. So x1 is equal to x, and x2 is equal to y. So when you have I and j both equal to 1, that's f of xx. So that's this term here. So we have 1/2 f of xx evaluated at 0, 0, and then x minus a1 and x minus a1. In this case, a1 is both 0. So it's x minus 0, which is x minus 0 squared. When you have I and j both equal to 2, that means you have f of yy. So that's this term here. So we have 1/2 f of yy evaluated at 0, 0. And then we have, again, our second variable, x2 is equal to y. So we have y minus a2, which is also equal to 0, times y minus a2. So that's my y squared. Then we also have, when we have the first variable, I is equal to 1, and j is the second variable, that's y. So f of xy. And then also the other way around, when I is equal to 2, that's y, and j is equal to 1, that's x. So f of yx is equal to f of xy. It doesn't matter which order we do the partial derivatives. So I have 1/2 for each, so then I have twice that, so that's just 1 times f of xy evaluated at 0, and then x minus 0, and then y minus 0. Those are my terms. So now I can plug in, and I'll have my f of 0, 0 we said was 1, f x at 0, 0, where's that? That's equal to 0 times x minus 0. F of y at 0, 0 is also 0 times y minus 0. 1/2 f of xx, which is minus 1, times x minus 0 squared, plus 1/2 f of yy, which is equal to 1, y minus 0 squared, plus f of xy, which is equal to 0, x minus 0, y minus 0. So in other words, we get 1 minus 1/2 x squared plus 1/2 y squared. And this is our second order Taylor approximation. Our next topic is the Hessian matrix, which is simply the matrix of second order partial derivatives. And now we can write our Taylor polynomial of second degree in terms of our Hessian. So we have f of a is equal to our gradient. This is our first order part. Our gradient times our h vector. And our h vector is simply, if we're in 2 dimensions, h1, h2 is equal to x minus a, y minus b. In other words, if we're centering around a, b, then it's x minus a, y minus b. Plus 1/2, again, there's our 1/2. Then we're going to have this H matrix times our Hessian matrix for that function, multiplied by our H matrix again. Here's an alternate notation. An example of using this Hessian, so if we have this function again, which we had done on the previous slide, evaluated 0, 0, we want to find the second order polynomial. So then we have f of 0, 0 is equal to 1. We take the gradient of f, our first order derivatives. This is with respect to x, and then with respect to y, we evaluate it at 0, 0. And next we do the Hessian matrix. So the first item in the Hessian matrix is derivative of x with respect to x. So here is our derivative with respect to x. So we're going to take another derivative with respect to x, and we get cosine x sine y. Now we're going to take the same derivative of f with respect to x, and we'll take it with respect to y, and we get sine of xy. Then we take this next term, and we take the derivative with respect to x, and then we take the derivative with respect to y. So this is our Hessian matrix. We evaluate it at 0, 0, we get -1, -1, and 0, 0. So now we can plug into our formula. It's f of 0, 0 plus df of 0, 0 times h, and again, h is our x minus a, y minus b, plus 1/2 times h transpose, this h, and then our Hessian matrix times h. And here you can see it plugged in. And I have my 1. This becomes 0. This is 1/2. And when I multiply this, I get minus h1 plus 0 for our first term, and then the second term will be 0 minus h2, and I'm going to multiply that times h1, h2, so this I carry over my 1/2, doing my matrix multiplication, I get minus h1 squared and minus h2 squared. So here I just plugged in for h1 my x minus a, and for h2 y minus b. So this is my final answer. Well, actually, because a and b is equal to 0, my final answer should be 1 minus 1/2 x squared minus 1/2 b squared, which is what we got with the other formula. For review, I have this problem for you to try to compute the second order Taylor formula for f of xy equals e to the x cosine y about the point 0, 0. I suggest you pause the video, give it a try, and on the next slide, I'll have a solution for you. Here's the solution to the problem. And that's it for this video. Thank you for watching. And then we're going to look at higher order approximations.